This is problem number 2 from the series packet, which we worked the first 2 sections in class, but I'm going to go ahead and rework the whole thing. So you're given that f of x is ln of 1 plus x cubed, and you're given the Maclaurin series for 1 plus x, and asked to write the first 4 non-zero terms in the general term from the Maclaurin series of f of x. So if this is the Maclaurin series for ln of 1 plus x, then the one for ln of 1 plus x cubed is what you get when you plug in x cubed into that Maclaurin series for x. So this will become x cubed, this will become x to the 6th over 2, this will become x to the 9th over 3, and this will become x to the 12th over 4. And when you write the general term, you can also simply plug in x cubed for the x here. So this would still be negative 1 to the n plus 1. This would be x to the 3n, because it's x cubed to the n, all over n. So this is the general term, and these are the first 4 non-zero terms. For part B, it tells you that the radius of convergence in a Maclaurin series for f is 1, determine the interval of convergence. Since this is a Maclaurin series, this is centered at 0. It should have been A, right? It should be B. So this is a Maclaurin series, and so it's centered at 0. And they tell you the radius of convergence is 1. So that means the interval of convergence has to go between negative 1 and 1. But what we don't know is the inclusion of these endpoints. So we have to test the endpoints to actually figure out they should be included in the interval. So let's start by testing negative 1. And you test the endpoints by plugging them into the x for the general term and checking whether that series converges or not. So when I plug negative 1 into that, I got negative 1 to the n plus 1. I'm replacing x with negative 1, so this is negative 1 to the n, all over n. Now, when I combine those powers, I get negative 1 to the 2n plus 1, all over n. And then if this is like the harmonic series. If it alternating harmonic series converges. If it doesn't alternate, it diverges, because it's just a harmonic series, and that's what harmonic series do. So the way to figure this out is plug in consecutive values of n and see if the sign on the negative 1 will actually change, whether you get odd powers and even powers bouncing back and forth. So I plugged in 0 here, I get a power of 1. If I plugged in 1, I get a power of 3. I plugged in 2, I get a power of 5. The power is always going to be odd, so this is like negative 1 over n. So this is just basically the harmonic series multiplied by negative 1, so it diverges. I want to test positive 1. That's going to come out as negative 1 to the n plus 1 times positive 1 to the n all over n, which comes out as negative 1 to the n plus 1 all over n. Now, if you send the index counting up by 1s every time here, you'll see that the sign of this negative 1 will change because the power will switch back and forth between even and odd. So this is actually the alternating harmonic series. So it converges. So when I write the interval of convergence, I would include 1, but not negative 1. Now, part C. Part C says to write the first 4 non-zero terms in the Maclaurin series for f prime of t squared. Okay, so if we're going to write f prime of t squared, we need first the first 4 non-zero terms of f prime. So I write f prime of x, and I tend to write approximately, simply because we're using an approximating polynomial here, the first 4 non-zero terms. This is what we have for x, right? For f of x. F of x was this thing we found in part A. So if I take the derivative of each of these terms here, this would give me 3x squared. This would give me minus 3x to the 5th. This would give me plus 3x to the 8th. And this would give me minus 3x to the 11th. So that's the first 4 terms of f prime of x. x. It was asking, though, for f prime of t squared. So I need to plug in for all those x's t squared. I think I got all that right. Now, then it says if g of x is the integral from 0 to x of this thing with respect to t, write the first two non-zero terms of the Maclaurin series for g and use it to approximate g of 1. So now I've got this g of x, sorry, g of t, right? G of x, well, g of x is my fault, g of x. And it goes from 0 to x of this thing I just found. Which means literally I would take the antiderivative of this thing, plug in x, and subtract what I get when I plug in 0. So the antiderivative of this thing would be 3/5 t to the 5th. And this would be 3/11 t to the 11th. And this would be 3/16 t to the, I said 3/16, 3/17 t to the 17th. And so forth. Now notice it only asked us to find, first 4 non-zero terms. So that's 3 of those, so I need to write the 4th one. So that's 3 over 23 t to the 23rd. And again, I probably should, approximate here. Now, don't get too caught up in the approximation symbols. That's not really all that important. So it says use the first two non-zero terms of this to approximate g of 1. So g of 1, using the first two terms of this, would be 3/5 times 1 to the 5th minus 3/11 times 1 to the 11th. So that's 3/5 minus 3/11, which is what, 55? That's 33 minus 15, so that's 18 over 55. Sounds right to me. All right, so here's that. This was an answer here. This was an answer here. This was an answer here. So part D says, the Maclaurin series for g, I when x equals 1 is a converging alternating series with individual terms that decrease in absolute value to 0, meaning it converges. Show that your approximation in part C must differ from g of 1 by less than 1/5. Clear language indicating an error. But with alternating series, unlike Taylor series, they're much easier to determine the error. In alternating series, the error is literally less than the next term. There's no m involved, it's less than the next term. So error is going to be less than or equal to what would be the next term after I stopped with my approximation. I stopped with the second term. So the error is going to be less than the next term. Right? So I got that. Now I wanted the error at 1. So if I find the error at 1, I get 3 times 1, 17, over 17, which is 3/17. And 3/17, without having to do too much hard math, is clearly less than 1/5. So you've shown what the question was asking for.